essay exam for essay 2. Today, just talking about the lungs. So, first off, just wanted to cover some anatomy and how the lungs work. So I'm just gonna draw super simple. Okay, I'll just do this. Okay, so the lung has two membranes, or there are two membranes within the lung. We have the parietal viscera, and we have with the parietal and the visceral what is it called? Pleura. Oh my gosh. Sorry, Aaron, that took me so long. It's okay, you're not even gonna watch this video, but I'm making it to help myself learn. So we have the visceral and the parietal pleura. The visceral is right on the lung, the parietal is on the rib cage. And so lungs themselves are elastic. They naturally want to fold in and collapse. So our body uses this cavity to maintain a negative pressure. So there's a negative pressure here that pulls the lung out. So what happens, we have the muscle here called the diaphragm. When it contracts, it pulls downward. That increases the space here. And then typically we also have a movement of the internal or external intercostals, which are going to lift your ribs upwards, creating a bigger space here, creating a larger negative pressure, which is going to enable you to breathe in. We also have the scalenes, scalenes and the sternocleidomastoid muscle up here that can pull up from your neck. And then as we exhale, as these spaces and muscles relax, the space gets smaller, the lung can then contract because there's less negative pressure or even maybe positive pressure. However, we can have internal intercostals. Oh, I spelled that totally wrong. Internal intercostals, which will pull the ribs down. The diaphragm will relax, these muscles will relax, or we can also have the abs, your rectus abdominis. This can also pull down, creating a smaller space, which is going to allow you to exhale. These muscles really are only used in a forced exhale. Most exhalation is passive, or it doesn't require muscles. So that's kind of how the negative pressure works. So as the negative pressure works, the space within the lung increases, and then stuff is going to come from outside. As this space gets smaller and the lung contracts, there's going to be a positive pressure in here, which is going to cause the air to move out of the lung. So that's what's going to happen. So we can get a thing called pneumothorax. A pneumothorax is when there's a puncture in the lung. So if somebody gets stabbed or something, they get a puncture in the lung. This is going to cause their lung to collapse. Their lung will be really small. Air will be able to move in and out of this pleural cavity, and that's going to disable the person from being able to use this lung for ventilation or for breathing. There's also tension pneumothorax, and that is when air can go in, but it can't come out. So when they inhale, the lung still collapses, but when they exhale, that pressure is maintained equally as bad. So let's move on. So I'm going to talk about inside the lung. So we have our lung here. We're going to draw one alveolus. So there are tons of little alveolus, but we're just going to use one, so I'll write alveolus. There are tons of alveoli in the lungs, but we're just going to use one for this demonstration. Actually, we're going to use two. So inside the lung, because of the constant movement of air in and out, it causes water to build up on the insides of the alveoli. So what happens is we have something called surfactant. Let's draw on some cells. They're going to release some surfactant. These are called pneumocytes type 2. And pneumocytes type 2 are going to release surfactant. Whatever. Surfactant breaks up water tension. So let's just talk about this really fast. Inside the lungs, this water, if we draw just the surface real fast of the water, right on the surface, we have these H2O molecules. Let's draw a difference in that. And they're forming what are known as hydrogen bonds, or a type of intermolecular forces. So as these water molecules do this, it creates tension, so they pull closer to each other. Tension. And this is referred to as surface tension. It happens right on the surface of the water. So in an alveolus, the water net force is going to be pulling the alveolus in to shrink it. Obviously, we don't want that. If the alveoli are shrunk, then they're not going to be able to have oxygen and CO2 exchange going within them. So what surfactant does is it's an amphipathic molecule, so it has one side that does a really good job of interacting with water and another side that doesn't like water, or a hydrophobic and hydrophilic end. It's going to stop and decrease tension. So this is where Laplace's law comes into play. He said that pressure is equal to 2T over R. So this is tension, or surface tension. And then this is the radius of the alveoli. So for example here, what this is saying, if they have the same amount of tension, excluding surfactant, what's going to happen is this radius is smaller. So that means this is going to have a higher pressure, while this alveolus is going to have a lower pressure because it has a larger R value. So because of this, if these are both in the same lung, we would think air is only going to go to the larger alveoli. However, because of surfactant, it enables both of these to have equal pressures. Pressure 1 is going to equal pressure 2. And so what that enables us to do is use small and large alveoli in the lungs to fulfill gas exchange. So if somebody doesn't make surfactant, for example, they're going to have an increase in surface tension, which will increase the pressure, which is going to make it harder for them to breathe. So surfactant's super important. And if it makes it hard for them to breathe, they could go into a state of acidosis, respiratory acidosis. So now we're going to talk about gas exchange. So while gas is in the alveoli, there's some oxygen molecules. We have the blood coming by. And so now we're going to have an exchange of gases. So I'm going to use purple to represent CO2, and we use green to represent O2. So just to cover this, O2 in the blood, 98% of it is transported on hemoglobin. And then there's 2% in the blood. With CO2, it's a little different. Most of it gets turned into carbonate, let's say about 70%. And then 7% is in the blood, and 23% is on hemoglobin. I'm not exactly sure if those are the exact values for CO2, but it's about that. The importance is it's mostly converted into bicarbonate, and this is mostly converted into oxygen, or transport on hemoglobin. So what happens is we have a partial pressure of oxygen here, because oxygen isn't the only thing in our atmosphere. And because it has a greater pressure here, it'll move towards equilibrium and diffuse into the blood. And hemoglobin, let's just draw a red blood cell. Hemoglobin inside a red blood cell will absorb that. So as it absorbs these oxygen molecules on its hemoglobin, what's going to happen, that will decrease momentarily the amount of oxygen here. So more and more oxygen will diffuse over so that more and more blood cells can get oxygenated. Then CO2 is going to have a higher pressure. It's going to have about 45 in the venous side, 40 in the arterial side. So 40 in this space, it'll be about 40 millimeters of mercury pressure, and carbon dioxide will come out and leave the lung. So we have an equation to help us represent this. So we have PaO2. So this is how much, capital A is pressure in the alveolus. So we know that the pressure in the alveolus for O2 is equal to the fraction of the pressure of O2 in the atmosphere times atmospheric pressure minus water pressure. And then we times it by PaCO2. So this is arterial CO2 divided by R. R is equal to VCO2 over VO2. So the volume of CO2 exchange for the volume of O2 exchange. In a perfect world, this would ideally be 1, but for us, it's typically 0.85. This almost always is 44 millimeters of mercury. This at sea level is 760. At sea level, this is 750 just 50 millimeters of mercury, and then this is typically 21%. This is very useful in a clinical setting because if we take somebody's oxygen, blood oxygen, or so this value here is going to match PaO2. So arterial pressure of oxygen and this will match each other. So for example, if somebody is on oxygen, let's say their PaO2 is 102, which is a normal amount, millimeters of mercury. If that person's on no ventilation, we know that they're okay. However, for example, if somebody is on a ventilation device, if somebody's breathing in O2 and we increase the FiO2 to 30% of their oxygen, or of the gas in the air, that is going to increase this value, which means this value is actually low. And so we can use that to clinically diagnose people who aren't receiving enough oxygen, who don't get enough alveolar gas exchange, and that can help us diagnose different problems and different lung diseases like bronchitis or emphysema or pleuritis or fibrosis, and that can help us understand the patients we're treating. So next we need to talk about CO2 and O2 transport in the blood. So now we talked about the exchange. So oxygen is mostly transported through red blood cells on hemoglobin. So I'm going to use this blue to represent hemoglobin. So as we talked about before, hemoglobin has 4 units, and each one of these 4 units has an iron in it that allows O2 to bind to it. So there are, however, 2 forms of this. So I'm going to draw 2 different examples. So if this is a T state, that is not right, a T state hemoglobin, and this is an R state hemoglobin. So in this one, the irons are on the inside. This one, the irons are facing outward. So what happens is in the T state, O2 is not going to bind. It's going to bounce away or it's going to be released. So if there's O2 on the hemoglobin, it's going to release. In the R state, however, O2 binds. So right in the lungs, right at this point, all hemoglobin is going to be in the R state because it's going to want to bond to oxygen. But as it moves throughout the body, these are going to shift from the O to the T, or from the R to the T state. Oxygen will be released to the tissue. So that's our tissue here. So we're going to get O2 released here. So there are some factors that the body uses to signal R state to T state. The first is CO2. CO2 can act as a binding molecule to cause a conformational shift, releasing O2. We get that from our cells, right? As they go through metabolic processes, the tissue will release the CO2, and it will cause this shift. Something else, if we increase the acidity, that can also do it. Or if we increase the temperature, they're more likely to favor the T state. Then there's one other molecule, it's called 2,3 BPG. So there's a 1,3 BPG from glycolysis. And then there's an enzyme called 1,2,3 BPG mutase, and that'll turn 1,3 to 2,3. Anyways, 2,3 BPG can also cause this change. It can change R to a T state. So what happens is red blood cells, the only type of metabolic process they can do is glycolysis. So when there's not enough oxygen, right, they're losing oxygen, it's going to signal the making of this enzyme here, going to make 2,3 BPG and cause more oxygen to be released. So this is happening in the cell as the blood moves out throughout the tissue. So we have a little graph to talk about this. So if we have I want to say this is pressure, or this is O2, PaO2. So arterial pressure of oxygen, and then this is the, I can't remember what the axes are. Let me look. Not that one. Next one. PaO2 and percent of hemoglobin saturation. Okay. Oops. Okay. So PaO2, pressure of oxygen, and then we have percent saturation of hemoglobin. Sorry, I can remember that. So this is the curve. Oh, that's a bad one. This is the curve. So about 60 millimeters of mercury. This is when it kind of starts to dive. So you can see here in this first part of the graph, a change in between 100 and 80. There's a really small change in the saturation. So hemoglobin is really good at staying saturated until it's about 60 or 40. Then it kind of takes a dive and we get a smaller oxygen amount in the blood. So what can happen here, we can have two lines that kind of mimic this. So this first one, this red one, if for some reason there's an increase in CO2, if there's an increase in H+, or you could say a decrease in pH, if there's an increase in 2,3 BPG, or if there's an increase in temperature, this is going to cause a shift, and naturally the hemoglobin is going to become less saturated, or oxygen is going to be released easier. So if your body's not getting enough oxygen, it's going to want more, it's going to release it easier. Then on the other side of things, if we have a decreased CO2, or a decrease in H+, or an increase in pH, those are the same thing. If we have a decrease in 2,3 BPG, or decrease in temperature. That's going to cause hemoglobin naturally to be more saturated. And it's going to make it harder for us to reach a point where our oxygen levels aren't where they should be. So that's kind of some of the factors that influence the affinity of hemoglobin. And those are the effects it has. This is known as the oxygen hemoglobin dissociation curve. But that's it for everything for gas exchange and how the lungs work, how it transports oxygen throughout the body, how the oxygen is released, and then some of the factors that can affect the oxygen hemoglobin dissociation curve. Thanks, Aaron.